the difference of two squares and Fermat-Bateman quadruples of power equal to 1. My motto: plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. The difference of two squares. Algebraically, we know that 1. The sum a plus b all squared equals a squared plus 2ab plus b squared. Euclid's Elements, Book 2, Proposition 4. 2. The difference a minus b all squared equals a squared minus 2ab plus b squared. Euclid's Elements, Book 2, Proposition 7. 3. The sum a plus b times the difference a minus b equals a squared minus b squared. Euclid's Elements, Book 2, Propositions 5 and 6. It is in this form, a squared minus b squared equals the sum a plus b times the difference a minus b, that the difference of two squares is taught. But this is only half the story, and we need to examine the binary partition of the integers and Fermat-Bateman quadruples of power equal to 1. Binary partition of the integers. If we take an integer, say c equals 11, then we can divide it into c equals b plus a and apply it as per the table to the difference of two squares. From column 2, the sum c plus b times the difference c minus b is equal to the sum c plus b times a is equal to ca plus ba. From column 3, the sum c plus a times the difference c minus a is equal to c plus a times b is equal to cb plus ba. Column 3 minus column 2 is equal to column 4. Therefore, cb plus ba minus ca plus ba is equal to cb minus ca is equal to b squared minus a squared. Both even and odd integers, 2n plus 1 and 2n, result in n binary partitions. Despite the arrays of numbers that follow, they are relatively simple to grasp. The colour code used for the numbers is red for a square and green for a pronic number, which is just the product of two adjacent numbers. Dividing a pronic number by 2 gives a triangular number, which are coloured blue. The number 6 is both a triangular and a pronic number. Starting with Fermat-Bateman quadruples of power equal to 1. 1. Take an odd number and split it into two parts with a difference of 1, which for our example is 11 equals 6 plus 5. Multiply through the resulting three-term equation by each of its terms to generate three composite triple equations, 2, 3 and 4. Substitute 4 into 2, 3 into 2 and 4 into 3 to give equations ABC, which are Fermat-Bateman quadruples of power equal to 1. Since every square is the sum of two adjacent triangular numbers, and every triangular number can be split into the sum of a perfect square plus a pronic number, it follows that every perfect square can be split into the sum of a smaller square plus a pronic plus a triangular number, as per the above algorithm. This slide and the next one show the triples and quadruples that result for the integer 11 for its 5 binary partitions, as detailed in sections A, B, C, D and E. The choice of the integer 11 makes the consistent numeric pattern and the progression present in each of the partitions clearly evident even to an untrained eye. What is blatantly obvious is that the three Fermat-Bateman quadruples rearrange to form three difference of two square equations, where we now have the sum of two composites instead of the more familiar product of the sum and difference terms. We note that the algebra of the rearranged Fermat-Bateman quadruples is identical to that which we derived in a somewhat trivial manner on slide 3. In section F, we have used the smallest primitive Pythagorean triple, 5 squared equals 4 squared plus 3 squared, which gives us the partition 25 equals 16 plus 9, with the final result being 3 Fermat-Bateman quadruples, where all terms are perfect squares and 2 of which are a fourth power, namely 25 squared and 9 squared. Only Pythagorean triples have this outcome. I have therefore called them Fermat-Bateman Pythagorean quadruples. Section G highlights the fact that the second and third triples in each partition combine to form the equation a plus b all squared equals a squared plus 2ab plus b squared, as given at the start of the video. Whilst the examples are all for odd numbers, the same is true for the even numbers, where we divide by 2 and plus minus 1, and the resulting triangular numbers obtained after squaring can both be split into a square plus a pronic number. The rest is straightforward as per the odd numbers. To reiterate, only when the integer forms a Pythagorean triple can we obtain the Fermat-Bateman Pythagorean quadruples with all terms equal to squares, as per the second half of section F. The table gives the difference of two squares as the sum of two composites as derived from the Fermat-Bateman quadruples. It has been conclusively demonstrated that 1. That every integer can be stated as a triple by splitting it into its binary parts, irrespective of whether it is or is not a power z to the n. 2. When an odd integer is split into two parts, n plus 1 and n, and an even integer into two parts, n plus 1 and n minus 1, it can be converted into 3 Fermat-Bateman quadruples, 2 of which consist of a triangular number plus a pronic number plus a smaller square, and are both equal to the square of the original integer. 3. Only Pythagorean triples result in Fermat-Bateman Pythagorean quadruples, where all 4 terms in all 3 equations are themselves squares, and 2 at least are a higher even power. 4. It is not possible to elevate a quadruple to a higher power, hence higher powers cannot have less than 4 terms that are all integers raised to that power. 5. Fermat-Bateman quadruples are just rearranged difference of 2 squares equations, and therefore allied to the Pythagoras equation, and cannot therefore be elevated to higher powers. The sequel to this video is Fermat's last theorem and Robert D. Carmichael's missed opportunity. Don't miss it.